Hi everyone! So today's video is about rotational inertia. So before we talk about what rotational inertia actually is, we have to see how it was originally or is just derived. So first, in order to do that, we have to talk about the kinetic energy of rotation. So we know that kinetic energy is the energy of motion, right? So we can't simply use that 1/2 mv squared that we already know, that equation to be kinetic energy, to express when we have a kinetic energy of a rotating body. The reason for this is that equation 1/2 mv squared is the kinetic energy of the center of mass of a rotating body, which if that body is just rotating, it's not moving at all, we call that translating. If it's not translating from one spot to another, then that 1/2 mv squared, that velocity of the center of mass is 0, and therefore there's no translational kinetic energy. That's what we call that. So we have to use a different equation for this. So in order to find the kinetic energy of a rotating body, we have to treat that rotating body as a collection of particles with different speeds. Okay, so what we do is we add up the kinetic energies of those different particles to then find the kinetic energy of the rotating body as a whole. So here's the equation for this. Okay, so we get 1/2 m1 times v1 squared plus 1/2 times m2 times v2 squared, and so on and so forth. Of course, if we have a bunch of different particles, so say something like, again, here comes my candle lit again, and this is rotating in place. Now what we're doing is we're taking the masses of all the different little tiny particles, so like all the different atoms in here. Of course, this is a continuous body, so we do something a little bit different with a continuous body, which I'll talk about in a second. But say we simplify and say this is only like 1, 2, 3, 4 particles or something, and those 4 particles are rotating about a central axis. We would have 1, 2, 3, 4 masses, and we would take the masses of each and then the velocities of each of those masses and then put them into this equation in order to find the kinetic energy. Of course, when we have a continuous body like that, we have an basically infinite almost number of particles, and so we want to use the sum notation. We're just summing up the different 1/2 times each mass times each velocity of each particle squared. Now, the problem with that equation is not all the particles are moving with the same linear velocity v. And we learned about this last lecture or last video, where the farther we are away from that rotation axis, the faster the linear velocity v is going. So what we do here is we're going to use angular velocity. So we know that they have the same angular velocity, which remember was that fancy W or the omega symbol, lowercase omega. So because they have the same angular velocity, sorry if you can hear Rowdy barking, we can use this equation that relates linear velocity to angular velocity with the radius. So because linear velocity is equal to angular velocity times radius, we can then plug that in for our linear velocity v in that 1/2 mv squared. And then what we do here is we just distribute this squared term to both the angular velocity and the radius. And then we get this right here, because again, each particle in that rotating body has the same angular velocity. So because of that, we can just use that one angular velocity and kind of factor that out. And then we get this 1/2 times the sum of each mass, each particle that we're talking about, times the radius or the location from the axis of rotation of that mass squared times the angular velocity squared. Rowdy's just barking like crazy. So this right here is a special thing, this mass times radius squared, and that's what ends up being our what we're talking about today, our rotational inertia. So the quantity in parentheses, this again right here, tells us how the mass of the rotating body is distributed about the axis of rotation. And we call this rotational inertia or moment of inertia. You'll hear both of these terms for this term. I don't know why we like to give certain terms multiple names in physics sometimes, but you'll hear both rotational inertia and moment of inertia. I will also use both kind of interchangeably, so I apologize if you get confused. These are the same exact thing, okay? So rotational inertia, or moment of inertia, it's just when we have a system of particles. So when we have something that's not a continuous body, something like this, but we have a bunch of particles that are rotating about a central axis, we can use this equation right here. So you get the sum of the mass of each particle times the radius of each particle squared, or that radius, remember, is the measure, that distance from where the particle is located to the axis of rotation. And then we can just use this equation for kinetic energy, and this is rotational kinetic energy, 1/2 times big I, which of course is our rotational inertia, times our angular velocity squared. So make sure you write those equations down. So rotational inertia, what it is it's a measure of an object's resistance to change in rotation. Remember that term inertia. Remember, we learned inertia is a property of matter, which means the more matter, the more mass you have, the more inertia you have. That's a resistance to a change in motion. So since we're talking about a rotational inertia, we're talking about an object's resistance to a change in rotational motion here. So what this does is it depends on the distribution of mass. So objects, you can see that have a large rotational inertia are going to have a large mass and or a large radius. So really what this means is the more mass that's farther away from that axis of rotation, the higher the rotational inertia, the harder this object is to rotate. All right, that's like the gist of the entire thing, okay? So, like I said, things with larger masses farther away from the axis of rotation have large rotational inertias, which means that they're harder to rotate. And it's kind of hard to picture this in your brain, but if you, this picture is a good kind of demonstration of how this works. Something like this is easy to rotate when we have more mass closer to that axis of rotation. Here, the person's going like this with like a dumbbell, trying to rotate that back and forth. So if the mass is closer to the axis of rotation, it's easier to rotate. If the mass is farther away from the axis of rotation, it's more difficult to rotate. I was working out the other day and doing like a medicine ball slam kind of thing, if you've ever done this. If you take that really far away from your body and you kind of try to slam it down, it's really hard to get it so like rotated around your body. But if you have it closer like this, it's a little bit easier. So if you have a medicine ball or you have a weight or something like that, try to do that. See how it feels, because you can see that once a mass is farther away, our R is larger, it is harder to rotate. You have higher rotational inertia. And then of course, if you have a small rotational inertia, it's easier to rotate. Now, when we have these rotational inertia problems, here's our game plan. So first and foremost, if we have a few particles in a specified rotation axis, we just use that mr squared for each particle and we add them all together to get the total rotational inertia of the object. If we need to find kinetic energy, like rotational kinetic energy, then we can plug that into the kinetic energy equation, that 1/2 I, rotational inertia, times omega, angular velocity squared, in order to find the kinetic energy. Now, if the rigid body consists of a great many particles, it's continuous and we can't use that above method because, again, if you're adding up the mass times radius squared of each tiny little particle, each little tiny atom in this, continuous body, it's going to take you forever because there's almost an infinite number of particles, right? So we have to use a different method, and in order to do that, we're going to replace the sum notation with an integral, and we define the rotational inertia as this. Our I, rotational inertia, is equal to the integral of r squared times dm. Now, this is kind of a weird equation because you have the radius squared, r squared, and you're evaluating with your mass and with respect to mass. So because of this, I'm going to have a whole separate video on how to use this equation to derive an equation for rotational inertia of a certain body, because I have seen it over and over again on the AP test that they have, the rotational inertia of a rod is this, use the rotational inertia equation to derive the equation for this rod or something like that. So I'll show you how to do that and how we use this equation. However, for now, I'm just going to give you a bunch of the rotational inertias that we will be using in class, and these are in your book as well. So like I said, the next slide gives the results for this integration for several common shapes. So here's our common shapes here. The ones that are really important are a hoop about a central axis, and all this is mr squared. You'll see that it's very similar to our sum notation, right? And that's because a hoop, we can just say that it's almost like a point mass, right? So just mr squared is our rotational inertia. This one is very, very important, the solid cylinder or disk about a central axis. You'll see a lot of problems with a disk being used, and this is 1/2 mr squared. Another really important one is the solid sphere about any diameter, that 2/5 mr squared. This one's really important as well, a thin rod about an axis through the center perpendicular to the length. That one is very, very important as well. I would say the thin spherical shell is really important as well, this 2/3 mr squared. So I would memorize those ones that I just mentioned. In class, I will tell you if you need to memorize anything else. But for the most part, I do see that you're given these things usually on the AP test, like on a FRQ. So don't worry about it too much, but I would memorize some of these just in case you need them in like a multiple choice question or something like that. And then the last thing I want to talk about in this lecture is the parallel axis theorem. So the parallel axis theorem has to do with an axis of rotation that's parallel to an axis through the center of mass. So if we know the rotational inertia of a rigid body through the center of mass, we can easily find the rotational inertia about an axis parallel to the axis through the center of mass. So here's the equation for our parallel axis theorem. The rotational inertia I for our new axis of rotation is equal to the rotational inertia I through the center of mass plus mh squared, where h is the perpendicular distance between the given axis and the axis through the center of mass. Here's a picture of this. Here, instead of h, they use little r, which is kind of confusing because sometimes r we also have as radius, which is why I didn't really like this picture specifically, but this is the best picture I could find online. So this is what you get. So right here is our axis through the center of mass, so our rotational inertia through the center of mass. And then this is our new axis of rotation, and that thing is rotating around like this. So this r is our perpendicular distance it's parallel from this axis of rotation to this axis of rotation, okay? So usually you're either given this rotational inertia through the center of mass, or you're given that it's a disk, or it's a hoop, or it's a blank. And so you know that like the rotational inertia of a hoop through the center of mass is mr squared. You know that the rotational inertia of a disk through the center of mass is 1/2 mr squared. So that's what you would plug that in here, and then, you know, sometimes they'll give you the perpendicular distance for your r or your h as well. And then m, of course, is just mass, okay? So this is the parallel axis theorem. Now, this is one of the few things, because usually you can, you know, use your equation sheet on the AP test. You can derive some equations from your equation sheet that aren't on the equation sheet pretty easily, but this is one that is not on your equation sheet that I would say is very, very important to just memorize. All right. A proof of this theorem is on page 275 in your textbook. I'm not going to go over the proof in class, but if you're interested, you can see that proof on page 275. And like I said, I do want you to memorize this equation. It is very, very important for you to memorize this equation.